Guys, welcome to Lab 4, Magnetic Braking with Faraday's Law. So the introduction and purpose. So what is the purpose of this lab? In this lab, we explore the interaction between a time-varying magnetic field and a conductive non-ferrous material, which we used aluminum foil. We then observe a falling bar magnet through the foil tube. And by observing that, we can validate Faraday's Law, which states that a changing magnetic field creates an electric field and therefore a measurable voltage, or simply put, a changing magnetism makes electricity. Using our computational model, we can visualize Faraday's Law. So the fundamental physics principles we used was Faraday's law in motional EMF. So the falling magnet in our experience creates a time-varying magnetic field. As the magnet falls through the tube, the magnetic flux through any given horizontal slice of the tube changes over time, which induces an electromotive force. We also use Lenz's law. The induced current creates its own induced field directly opposing the change in magnetic flux that is created. So above the magnet, the downward flux should decrease, inducing a current that flows in a direction that strengthens the downward field. And below the falling magnet, the downward flux is increasing, so the current flows in a direction to oppose it at that point, and it points upwards. We also use the Biot-Savart law and Newton's third law. We use Biot-Savart law to determine the force exerted on the current carrying rings by the magnetic field of our falling dipole. Newton's third law says that if force is exerted, an equal and opposite force must be present. Thus, we can assume that if our magnet exerts a magnetic force on a current carrying ring of aluminum tubing, the ring must exert an equal and opposite force upwards on the falling magnet. And then, of course, we use dynamics and motion, Newton's second law, that basically sums all forces together. So we can assume that with the counteraction force and the actual force itself, everything should sum to zero. Checkpoint. Why can't we use a ferrous tube? We cannot use ferrous tubes because the tubes interact too strongly with the magnet. Ferrous materials have a direct magnetic attraction, which would cause the magnet to stick to the tube rather than falling through. Foil is conductive, but not ferrous. It only interacts with the magnet through induced electromagnetic currents, which allows us to isolate the effects of Faraday's law. Experiments and setup. For this experiment, we used an aluminum tube and a dipole bar magnet. So the length of our tube was 0.235 meters with an inner radius of 0.015 meters and a foil thickness of about 0.0187 meters. Checkpoint. Data. What happened to the magnet? How does this compare to a magnet falling in free space without a tube? Because there is no tube and our magnet falls in free space, acceleration downwards is at approximately 9.8 meters a second squared. There's no opposition to gravity. In our aluminum tube, however, our magnet experiences an upwards magnetic force, which slows down the magnet's descent. Inside, it should reach a near constant terminal velocity rather than consistent acceleration. In free space, our magnet falls at about 0.22 seconds over the same distance, where d is equal to 1/2 gravity times squared. In our aluminum foil tube, the fall is slower, averaging about 1.86 seconds, because the induced current creates an upwards magnetic braking force that opposes the motion caused by gravity. Computational model. We start by defining our initial conditions with our experimental conditions, entering our given lengths of 24.5 centimeters, our inner radius of 1.5 centimeters, and a foil width of 1.87 centimeters. We also use the magnet's mass of 23 grams to calculate the magnetic dipole moment of approximately 2.166 amps per meters squared. Now we can define the core equations, the electromagnetic equations. The function dipole B calculates the magnetic field vector of our magnet as a dipole with a standard dipole equation. The calculated d flux dt and analytical function finds the timed derivative of our magnetic flux through each individual ring as our magnet is falling. Finally, this loop couples the physics together at each step in time. Using Faraday's law and Ohm's law, we can calculate that the induced current in each ring by dividing the induced EMF by the ring's calculated resistance. We can use the Biot-Savart law to then calculate the magnetic force exerted on each ring. Then, using Newton's third law, we can find the force exerted by the ring back onto the magnet. We then sum all of these forces over the entire ring to get the net upwards magnetic braking force acting on our magnet. These are the results of our computational model as a graph. Now, interpreting our simulation. So this is the simulation we've created. On the right is a model that demonstrates the magnet falling through the cylinder. In our graph, you will see that the very first second we release from rest, the velocity curve starts with a steep downward slope. This is because the magnet is initially in a free fall state, and gravity is our dominant force. The rate of change of magnetic flux through the distant aluminum rings is too weak to oppose it. However, when the magnet enters the top of our aluminum tube, the model shows that the creation of the induced current flows in the opposite direction. Below the falling magnet, the top blue ring shows a current flowing in the opposite to oppose the rapidly increasing downwards flux, while above the ring indicates a current trying to maintain the decreasing downwards flux. What can we conclude from this? As our magnet falls through the tube, our magnet reaches a terminal velocity due to the influence of both gravity and the magnetic flux induced EMF. The forces cancel one another, and the total force on the magnet should be zero. What ifs? What if the resistivity of our tube were reduced to zero? The change. When reducing resistivity to be zero, there would be zero electrical resistance. Our tube would become a superconductor. This would result in an induced currents in the tube to be extremely strong, creating a massive upwards magnetic force that perfectly fights gravity, causing the motion of our magnet to completely stop and levitate. So compared to our current setup, the magnet would not fall, it would hover in the tube itself. In our simulation, the magnet is still falling because our resistance is still high. This concludes our final lab of the semester.